All right, well, let's get started since we're the end of the day, and I'm sure everybody's excited to get to dinners and drinks and all kinds of fun stuff. First of all, I'm Jeff McVeigh. I'm with Intel. I'm responsible for our supercompute business, or HPC business. As always, it's great to be here with you. Also have a lot to talk about, and I apologize if I look a little damp. I got caught in the rain. I went for a walk before this, and I didn't check the weather beforehand, so I apologize for my appearance, but it will keep me fresh, I guess. So with that, let us get into our topic on AI-accelerated HPC. We won't bore ourselves with the legal disclaimers, but let's get into the environment that we're looking at. And the refreshing rain and the experience of Hamburg really brings out to me that it's truly great to be alive, and it's truly great to be part of this thriving scientific computing ecosystem. From my standpoint, we are experiencing one of the most transformative eras for this ecosystem. We're all familiar with the compute demands of traditional HPC, where we want faster, shorter time to solutions and more sustainable outcomes. But that rate of change is accelerating. And I think it's at least hard for me to imagine just 12 months ago that this type of explosion in AI would have taken over the broader ecosystem, not just this type of community that has been pushing the envelope of computing for decades, but everyone. My family members, it's much easier to talk about computing these days when everybody's talking about ChatGPT and the evolution of large language models, where we're seeing tens of millions of users on a daily basis for conversation, for exploration, for finding out new domains. And I think the possibility for change is extreme. And I think that change will hold the same for HPC. We already know that there's a lot of AI-enabled HPC for climate and weather modeling, for drug discovery, for high-energy physics. And I personally, I'm sure many of us have done this as well, use ChatGPT for develop some code samples for me. And I personally was very impressed, surprised by typing in something maybe a little esoteric. Provide me a SQL-based routine for an astrophysics module, and very impressed with the quality of the code, the readability of the code, the ability for that to run across architecture. And this really, in my mind, has the possibility of transforming the development as well as lowering barriers for GPU-accelerated codes. Now, we know that there's this synergistic relationship between AI and HPC. We're seeing the opportunities for dramatically reducing the number of iterations for an experiment by using hyperparameter optimization. We're also seeing the design principles of large-scale supercomputers being applied to large-scale AI systems, like the Azure system with 2,500 CPUs, 10,000 GPUs, and large rankings in the latest top 500 lists. We'll see the same thing with AI numerics being able to dramatically improve the speed of simulations and utilizing HPC libraries to accelerate AI. So all of this is a spiral of innovation generated by these two worlds colliding or enhancing each other. Now, if we look at the taxonomy of different computer systems, it's important that there is still a clear separation between them today. What I'm showing here is the trend over the past 5 years for the top 500 list, for HPC systems, obviously. The light blue represents CPU-only systems, while the darker blue represents GPU-accelerated systems with different levels of GPUs per node. As you can see, the trend line for CPU-only is decreasing pretty linearly here. 42% in the list released this morning. And we're seeing more and more growth of those that are at greater than 4 and 6 GPUs per node. But if we take that slice for just this last submission, or this last results from today. And we look at it for each of those domains for how much share are they for those top 100 systems. Again, 42% for the CPU only, a substantial amount for 6 or less GPUs, and then a growing amount for greater than 6 GPUs, and 0 for AI-accelerated systems. But for AI systems, the picture is quite different. Much fewer CPU only, much greater number of systems that have greater than 6 GPUs per node, as well as a growing predominance of specialized AI accelerators. This could be TPUs from Google, Trainium from AWS, recent announcements from Microsoft for them designing specialized AI accelerators, and others. So we see that there's a difference, even though there's a lot of similarities between these systems that are also being designed with different topologies. And if we look at this, and we ask ourselves, if you follow my thesis that HPC and AI are converging, that they are leveraging and synergistic to one another, but that the systems are designed differently today, how do we unleash the full potential of the future? What are those common design patterns? How do we handle diverse architectures from different vendors and different node configurations? And that's what we're going to be talking about today. And from my standpoint, we have 3 main layers of this stack that we need to address to help solve the world's most demanding technical challenges. At the bottom is where we're going to start, is the underlying compute hardware that can power both today and tomorrow's AI accelerated HPC codes. On top of that, we're going to need software that can unify, make it easy to get productive performance on that hardware. And finally, we need to deliver at scale with a reliable and resilient supply chain. So let's jump right into that hardware. So from Intel's standpoint, we know that there's a diverse set of workloads. And those workloads require a diversity of hardware offerings. We have CPUs, recently released GPUs, FPGAs, as well as AI accelerators. And this spans the entire portfolio of Intel's products in the data center, and I'm going to focus on the 3 middle rows for our conversation today, and in particular starting with Xeon, a powerful, proven CPU with literally billions of lines of optimized code to power this ecosystem as well as many others. It's able to deliver at scale, and in particular, we have 2 flavors of the processor, one known as an E-core for efficient power efficiency, and the other, the P-core for performance, which is really what is mostly used in the HPC space. Now, Xeon, as I mentioned, has been around for multiple generations. The most recent is known as the 4th generation, previously known as Sapphire Rapids. This product was launched in early 2023, already has over 400 design wins, being deployed by top CSPs. It's shipping and broadly available today. I'll also note that this processor was selected by NVIDIA to be the head node in their H100-based DGX system. The naming convention is probably pretty obvious here. The next generation, 5th generation, codenamed Emerald Rapids, will be available later this year. It's on track. It's sampling today. It will also utilize the same platform that the 4th generation platform product did to minimize cost and time to market. And finally, we didn't name it, but I guess you can probably guess what the generation will be. Granite Rapids will be the first P-core available on Intel 3 process technology, and will be available for delivery in 2024, providing substantial benefits on performance and I/O. Now, the question is, how does this perform on workloads, not just the availability and the specs? What I'm comparing here is versus Milan on a variety of HPC codes, 27 in particular, across 7 different domains, on average getting 1.5 better performance. Now, I know Milan's not the latest and greatest from AMD. Fortunately, at least for us, it's been extremely difficult to get our hands on any Genoa systems. Maybe we're not on Lisa Su's top priority list. But maybe that can change in the future, and we'll be happy to share and update these with that performance versus the latest from AMD. Now, it's one thing for me to talk about the performance, but it's more important for our customers to do so. Let me have Elizabeth Leher from BP provide their update on what they're seeing on the 4th generation Xeon processor.
BP and Intel have a long history of collaboration to deliver the high-performance computing capability needed to support our seismic imaging and other technology research programs. Earlier this year, we brought in a new cluster based on Intel Sapphire Rapids processors and had it up and running within about 3 weeks of delivery. Lenovo's direct liquid cooling system gives us the performance growth that we're looking for while maintaining our energy savings and sustainability goals. The new cluster has the highest gigaflop per watt performance in the center, meaning for the same power consumption, we're getting about 8 times the application performance than the older system that we've replaced. We're also in the process of upgrading the system to Intel CPU Max processors, and we're expecting another 1.5 to 2x speed up of our most intensive applications. Our HPC capability underpins many of the research breakthroughs that have been critical to growing our business.
So, great results. Excited for both the 4th generation Xeon processor, as well as which Elizabeth referred to as Xeon Max, and that's where I want to transition to next. This product, also within the Xeon product family, leverages and utilizes the same 4th generation architecture, but is targeted at solving one of the most fundamental problems that we face for HPC codes, and that is feeding the compute with enough memory bandwidth. We all know that the compute, the number of cores, has grown at an extreme rate over the past decade, but memory bandwidth has not kept up. And this is holding back the availability of those codes to be fully accelerated to the same level as the core counts increased. So earlier this year, we launched Xeon Max, which is the first and only x86 CPU with high bandwidth memory integrated. 64 gigabytes of HBM2E, so up to 2 gigabytes per core of memory. It has multiple memory configurations. You can have a system that has only HBM memory, no standard DDR DIMMs, especially if your workload fits completely within either that 64 or 128 gigabytes of HBM2E in a 2-socket system, or a caching mode where you can utilize both system memory as well as the integrated memory to have great performance. And a key part of this is that for most of those codes, they require little to no change to deliver great performance. Now, we're also committed to further expansion in this swim lane of high memory bandwidth processors. The next generation, as I mentioned, Granite Rapids product line, will also integrate system-level technology to increase the performance or the memory bandwidth across the full system memory using multiplexer combined rank DIMMs or MCR DIMMs. Now, this is technology that Intel innovated, developed, but is donated to JEDEC so that others can be standardized and deploy into the marketplace. The whole goal here is to making sure that we're balancing not just the integrated memory bandwidth, but the broader set of the performance on those platforms. Stay tuned as the Granite Rapids product comes out to see the capabilities of MCR. But let's get back to the here and now. So now I am comparing to a Genoa system for HPCG, a good proxy for memory bandwidth bound workloads, and seeing 65% better performance versus Genoa for the Xeon Max. And this really, as you can imagine, is in spite of the fact that Genoa has a much higher core count as well as 12 channels of memory. Looking across more broadly, a set of HPC workloads across 7 different domains, we're looking about a 2x average performance benefit over Milan X. Yay! Thank you for that. For a large portion of users, we feel that this really will be a game changer. And again, I'd like to introduce now Push Patel from Altair to talk about their experience for using Xeon Max. How you doing?
Thank you, Jeff. I'm doing well.
Excellent, excellent. So can you just give a little summary about the software package and the workload that you've been working with?
Yeah, absolutely, Jeff. So first, I want to congratulate the Intel team on this fantastic launch. I'm very proud of the long-term partnership we have with Intel. We've been working together on the simulation software as well as our HPC middleware like PBS Professional. So Altair, for those of you who are not familiar with us, we are a global software company focused on the convergence of high-performance computing, simulation, and data analytics. Within our software portfolio, we have over 150 different titles, including many solvers, which are very computationally intensive. One of the applications in our portfolio is AccuSolve. And this is a computational fluid dynamics code that is well known for its extensible architecture, its accuracy and robustness, and it's for multi-physics capabilities. AccuSolve is used by many customers in a variety of verticals for their product design and for their simulation modeling.
Perfect. What was your experience of porting the code to Xeon Max?
Actually, that was the fantastic thing. We didn't have to spend any time, development effort, to do the porting. It just worked out of the box, and we were able to see fantastic performance from that.
Can you share any of the performance gains that you're able to achieve?
Yeah, absolutely, Jeff. So first of all, AccuSolve is a memory-bound application. It is the perfect fit for HBM. We have seen performance gains of over 2x versus previous generation processors.
That's fantastic. Well, we're so excited that you were able to get such great gains with limited porting effort, and really excited for this product to be out in the marketplace.
Yeah, thank you very much, Jeff.
Thank you so much.
Congratulations again.
Thank you. Okay, so that was for the Altair package. Let's look at a few other examples of workloads here on Earth system modeling, looking at the scalability. So it's not just for single node performance, but also going up to 8 nodes, getting near linear scaling for the HBM only mode at 99% and the caching mode at 91% efficiency. Another key workload, as I was talking about in the very beginning, are all the generative AI and large language models. Here we're looking at performance for GPT-J, the 6 billion parameter model, and the 4th generation Xeon, without the integrated HBM memory, has instruction sets for accelerating AI workloads, AMX instruction set. And we get great both throughput as well as latency via those instructions. However, because of the large size of these models, they really lend themselves and require us to have that balance of performance from the core count as well as the memory bandwidth. And we're seeing 2x better performance on the inference throughput as well as 40% lower latency via the Xeon Max versus the 4th generation Xeon. Now, TAC also had done a study on their own in terms of the value of HBM memory with the Xeon processor. The question at hand here was, do GPUs get most of their gains from having that very high memory bandwidth? And as you can see here, versus their prior generation system, getting 2.5 better performance via the deployment of Xeon Max. So, before I move on to our next platform, our next compute swim lane, let me summarize the Xeon results. CPUs are foundational for all platforms, be they either the standalone 42% of the top 100 or the GPU accelerated ones, where you need the best CPU for those AI, the head node for those AI systems. Xeon has proven itself to be that choice. But we've expanded. We know that many workloads and deployments require focused operation on AI training and inference, and that's where the Habana and Gaudi product line come into play. I'm excited to show you the Gaudi 2 processor, OAM module, here. That includes 96 gigabytes of HBM2 memory, 24 tensor processor cores, 24 integrated Ethernet ports, and is built on 7nm process technology. Now, you can look at this and have deployments utilizing on-prem with Supermicro-based servers, as well as the Intel Developer Cloud, where we have deployments of Gaudi 2 to allow for developers, ISVs, and others to both try before you buy, as well as doing large-scale training and inference deployments utilizing that service. And as we look at the performance of this, now this is against the broadly available A100 from NVIDIA, we see significant gains across every stage of the AI lifecycle, from training to inference, from models like BERT to BloomZ with 176 parameters, and we're seeing all this translating to much better TCO and performance per watt, 60% better on that very large scale model versus the A100. And this is not just at the single node level, but also scaling across up to 64 nodes, seeing 99% scaling efficiency for stable diffusion training. So, fantastic work. The product's available in market today, and the follow-on generation will be available next year. So we continue to advance on each of these swim lanes for the product. So, I've talked about the CPU, I've talked about the AI dedicated accelerator. Now let's focus our attention on the GPU. We call it the Max Series GPU. You might see some naming familiarity here. Previously known as Ponte Vecchio, the Max GPU was launched earlier this year, has over 100 billion transistors, 128 Xe cores, 128 gigabytes of HBM2E memory. It also provides clear balance between an HPC focused system with 52 terabytes of peak FP64 support, as well as very strong AI numeric performance. It's not just an HBL-focused machine, but one that's really balanced to support both current and future workload needs. Now, the team and the broader ecosystem have been doing fantastic work enabling a broad set of applications to run on the Max GPU. From life sciences to physics to manufacturing, we have over 100 codes that are running on PVC, and many of them performing extremely well. We're making similar progress on AI models. We have popular ones like ResNet, BERT, Cosmic Tagger, all performing well on PVC, and we're continuing to make progress on some of the generative AI models like Stable Diffusion and Bloom. But let's see how this stands up from a performance standpoint. Here we're looking at an AI-accelerated HPC code, the high-energy physics 3D GAN, which uses generative adversarial networks to map particle paths. We're seeing 50% better performance than H100. Now, I will point out, I don't want to hide anything in the small print, this is a PCI Express H100 card. Now, again, Jensen just hasn't been providing me with enough of the higher-end products, but as soon as we have those in our hands, we'll be happy to give updates on the performance for those. But enough of my babbling. Let's have Prith Banerjee, the CTO of Ansys, provide their update on what they're seeing with the Max GPU.
Thank you, Jeff, for allowing me to speak during your keynote. Ansys and Intel has been partnered together for the last 2 decades in the area of high-performance computing to accelerate our solvers. For example, our latest collaboration is with Fluent, our CFD solver, that we have been able to get about 2x performance improvement on your latest generation Max CPUs from Intel. And that's because of the high bandwidth interconnect that you provide. The second collaboration that I want to talk about is our work on AI machine learning. AI/ML has been used recently by us to accelerate our solvers. For example, the work we have done with CoML Sim takes our auto-encoded versions of a 3D Poisson equation, and using the Intel optimized TensorFlow implementations, we're able to see this CoML Sim code run about 60 to 80% faster than on competitors' GPUs. So we are very excited about that collaboration. Thank you very much, Jeff, for asking me to speak today.
Great. Okay. So those are some of the AI accelerated HPC codes. Let's look at some more traditional HPC ones. Here we have a quantum Monte Carlo QMC pack code, 10 to 20% better, and with auto dock utilized for automating docking of small molecules such as drug candidates, we're seeing significant gains again versus the H100. And as we look across a broader set of workloads, we're seeing on average 1.3x versus that competitor product. Now, I will point out, if you're astute and looking at some of the numbers there, that I didn't cherry pick and only show those that were better than the competition. Some we have more work to do. Some in particular in the life and material sciences. Lamps is an example where when this snapshot was taken 2 weeks ago, we were 92% of the H100. But the advances on the software continue, and they continue rapidly. Since then, we're now surpassing that performance on the Max series GPU. Now, we've launched with our OEM partners and bringing those out more broadly in the marketplace, a few different configurations of the Max GPU. PCI Express cards, a by-4 system or UBB system. I'm very pleased to announce that we also have a by-8 configuration that will be soon available in the marketplace that'll be highly tailored to AI deployments. And for that, I'd love to introduce Ray Pang from Supermicro to walk us through their platform. Hey, Trey. All right, Ray, what do we got here? This is a big baby here.
Yes.
Tell us what's in this
Indeed.
big.
This is the industry's first 8 PVC OEM system. So, yes, this is the industry's first. At the top for you, that's the GPU tray. That contains 8 of the PVC OEM modules. This actually is a tray taking out. I'm taking 2 heatsink out. It's actually 8 OEM Max GPU there. So, as you guys know, the Max GPU has 128 gigabyte of HBM memory on board. So with 8 of them in a single system, this system can deliver 1 terabyte of HBM memory to handle the largest AI models and the HPC workload.
And that's just for the GPU tray.
That's one GPU tray.
That's right.
Alone.
And then what's on the bottom tray?
Well, at the bottom, that's a CPU tray. So as you guys see here, it has 2 different thermal zones. In this CPU tray, you can put in the Max CPU to even further enhance the performance. So at the top, that's the Max GPU. At the bottom, Max CPU. So this system is really designed to deliver the maximum performance.
Yeah. And why did you settle on this configuration?
This is really a well-designed system with balanced architecture. There's no blocking, there's no performance bottleneck in the system. As you guys can see here, in the front, there's plenty of NVMe drive base. So each of the Max GPU can be paired with 2 NVMe drives for fast local storage. At the back, you can now see, but trust me, there's 12 PCI Gen 5 expansion slots. So every Max GPU can have its own high-speed NIC for fast data in and out of the system. So even for the AU form factor, this is the perfect balance between thermal efficiency and space.
That's great. What type of customer demand are you seeing so far?
Well, we see tremendous demands from customers all over the world. They can't wait to get their hands on this system.
Or how can we order one?
First of all, let me talk about availability. This is the air-cooled system. We will make it available in July. In parallel, we're also developing a 4U liquid-cooled system that's going to be available in September. So if you are an existing Supermicro customer, you should reach out to your Supermicro contact and ask about the system. But if you are new to Supermicro, feel free to reach out to me, and I promise you, I will make the right connection.
And be down the booth as well. Thank you so much, Ray. Great partnership. Thank you. So that's the 8-way system there. I'll just kind of break it down. So here's one of the OEM modules without the heatsink on it. We also have the PCI Express card. And then as I walk across the stage here, also showing the Lenovo by-4 subsystem as well, that really show the full portfolio of the product line for the Max series GPU. So When is all this stuff available? Ray just talked a little bit about the Buy 8. We've been in what I would classify an early access mode. We've had silicon itself. We're working through to make sure that the full systems are reliable, we can scale, and we're looking at those beginning to go more broadly in the Q3 timeframe of this year across all the products. We're also, as we also have done with the Gaudi product line, bringing those out and deploying those more fully within the Intel Developer Cloud. Okay, so been talking a lot about that foundational level, talking about the existing products that we have in the marketplace today. But we really need to talk about what's next. And if you've been following some of the news from Intel recently, we made changes in our roadmap. And I want to talk about those, get that elephant out of the room here. Before I do, though, I want to take a little bit of a break from all the specs and the products themselves and talk a little bit about some philosophical elements. One, I love the outdoors, including mountaineering. When we're going up and climbing to reach a summit, there's often multiple routes to get there. Those routes are chosen based on your skills, the aesthetic beauty of it, the objective hazards that you're willing to tolerate. And the same thing is approached for these different computing systems. CPU only, GPU accelerated, AI-based accelerated solutions, different paths to the summit. And when you're climbing a mountain, it's important to understand the environment that you're in. Job number one is get home safely. And sometimes the summit might be unreachable that day because the weather's socked in, it started to snow, there's thunderstorms, and it's better to turn around and wait for a future time to reach that summit than just push forward. And the same thing applies to making architectural changes for products. You want to do it when the time is right, when the ecosystem is right, and not take a risky maneuver just because you said you're going to attempt a summit with some of your friends. There's been a lot of talk about CPU and GPU integration from Intel as well as others in the ecosystem. And honestly, I was one of those ones that's been doing a lot of that talking. But the decision to integrate or not needs to be based on the maturity of the workloads and the ecosystem that we're operating within. As we started this talk, a lot's changed in the past 12 months. Generative AI is transforming everything. And from our standpoint, from Intel's standpoint, we feel it is premature to be integrating the CPU and GPU for the next generation product, because that fixes you into a CPU and GPU ratio. It fixes you to the vendors of each of those products. And instead, we feel that the broad, dynamic nature of this market dictates the need for having discrete solutions. That's exactly why we've decided to have our next generation product be a traditional GPU. I'll admit it, I was wrong. We were moving too fast down the XPU path. We feel that this dynamic nature will be better served by having that flexibility at the platform level, and then we'll integrate when the time is right, when those workloads become more mature, when we better understand the right ratios between those compute elements, and we can do that effectively. So that's why we've changed course, and I wanted to explain that a little more fully. So, Falcon Shores, the GPU, targeted for 2025 product introduction. We will be bringing together the IP that we have in our Gaudi product line, deep systolic arrays, AI performance, scaling with standardized Ethernet to go very broad systems. We bring that together with the XE GPU IP for programmability, for FP64 support. This will allow for, at the platform level, flexible CPU and GPU ratios, a mix and match between vendors, and familiar GPU programming interfaces. We also utilize CXL in the platform to allow for better programmability, as well as memory expansion across them. So, that's the rationale, that's the reasoning, that's the background of why we've made this decision and clarified and changed our course with Falcon Shores. But we are very excited to bring that to market and deliver that value to this community. Okay, so I spent a lot of time on that compute layer. Now we got to get to the software. And that is a critical element for us to be able to scale those products. You saw a lot of diversity in the silicon, not just from us, but from many others. And the question is, how do we get the most value out of that silicon? Now, I'll say there's some evils in the world, and I won't talk about all the sociological or societal evils, but one of the evils that I find is proprietary systems. They lock you into a certain vendor that becomes very difficult to make changes. And our approach is the opposite of that. It's all about providing open ecosystems that provide choice and compatibility, to do that in a trustworthy manner, and to do that with a reliable and secure supply chain. And that is exactly where OneAPI comes into play. While we initiated this a few years ago, it is now community-driven with an open governance model. The momentum of this is building every day. The industry spec allows for choice while also providing productive performance across architectures. One example of that, LRZ had their DP Echo code initially in Fortran, worked with them to port to SYCL, and putting aside the actual performance numbers, showcasing that this runs well, functionally, with high performance across NVIDIA A100, H100, as well as Intel Max GPUs, to showcase the true portability of this code. But again, better for me to have others talk about it than myself, so let me bring on Hartwig Unz from University of Tennessee at Knoxville to talk about his experience with OneAPI.
Thank you, Jeff, for having me.
Absolutely. So can you explain to us how you're using OneAPI?
Yeah, so I'm the director of the Innovative Computing Lab. Some of you may know that. And what we are doing is software. So we are writing math libraries and tools for high-performance computing. And I think there are two important aspects that we drive forward. One is behind most of the simulation algorithms, at some point you need numerics, and we are providing these numerics. And the other point is that often it's the math libraries that are actually spearheading when there is new hardware, when there's a new software ecosystem, actually spearheading, looking into this, and getting new users onto this new software ecosystem.
And exactly why is SYCL in itself interesting to you?
SYCL is interesting for several reasons. So one reason is exactly what you explained. SYCL is an open thing, is an open standard, and it's running on different architectures, not only Intel GPUs, but also CPUs, architectures from different vendors. And that is exactly what the community wants. The community doesn't want to be locked into one vendor and then rewrite all the code when they get a new system. And the second reason is, I guess, that it has some characteristics in terms of being an asynchronous task programming model that is very attractive for many applications. And when we heard, we are part of the US XSK computing project, and we heard that the Aurora system will come and that it will have Intel GPUs, of course it was natural for us to look into the SYCL ecosystem.
Perfect. Briefly, how did the porting experience go for you?
Well, Intel was so kind to actually provide a porting tool. So that is what you do not always see, and that was very useful. I guess we were one of the early adopters, and we had to fiddle around a little with it. But Intel was very helpful in providing advice, and they actually took also our advice in terms of what needs to be changed, maybe to make it easier to use it. And that was actually useful to port maybe, let's say, 80% of the code. A second step is then the fine-tuning, and that has to happen in the SYCL programming model. But it was a very successful thing. So I would say it was probably like 12 months of a PhD student.
Oh, great. Anything, final comments on the OneAPI community you want to share?
Well, I would say currently the community has a lot of momentum, and the community is really excited. And you see that many people in the community actually go the extra mile. So they do not only do what they get paid for, but they think like, hey, SYCL is a really cool thing, and I want to try this out on a different platform, for example. And this is why I think SYCL will have a good future.
Perfect. Thank you so much, Hartwig. Great to see you. Thank you. Okay, so we have had a lot of progress. The ecosystem was launched a few years ago. We've been evolving the specification, working with others to do that, integrating within key frameworks like TensorFlow and Julia. In a short time, this truly has moved from a vision to a reality, and we know the work continues. From an Intel standpoint, we provide a comprehensive stack across not only the One API implementations on Intel hardware, but some of the tools that Hartwig mentioned in terms of code conversion, as well as making sure those work well with other standard languages like our Fortran compilers and our vTune performance analyzers and so forth. Okay, coming to the final chapter in our pyramid here. How do we deliver at scale? It's not just about the compute itself or the software, but we need the full systems. And I'm sure many are very familiar with the Aurora system, one of the most largest scale systems under development today. We're happy to announce that we've delivered over 10,000 of the physical blades themselves, each of those populated with 2 Xeon processors plus 6 Max GPUs. And for the first time, we're now announcing the full system specifications. 166 racks, 64 nodes per rack. That gives us a 10,624 total nodes. Multiply that by 2 to get the number of CPUs, by 6 to get the number of GPUs. We started the deployment utilizing the 4th generation Xeon processor and have been upgrading those to the Max, Xeon Max. About 75% of those blades have been upgraded to the Max CPU. You can see very large amount of system memory as well as storage. But again, what does the performance look like? So just to give you a few examples of some of the early codes running on this in comparison to both Polaris A100-based systems as well as Crusher with MI250-based systems, we're seeing great performance. Here with a speeding up fusion reactor prediction, you can see the performance benefits of those individual products, but then also looking at multi-GPUs. So roughly there's 6 Max GPUs per node versus 4 on the other systems, and we're getting roughly equivalent performance for 3 GPUs versus 4 on the others, and obviously gains as we go up to the full 6 on the Sunspot, which is the test bed for Aurora itself. Last hour, there was a full deep dive on many of these workloads that are scaling across Sunspot and the Aurora blades. I won't duplicate them here, but we're seeing very substantial gains, 1.4, 1.6x, 2x, not only at single node, but at many, scaling to many nodes as well. And we're excited to build this out, stabilize the system, and bring it to full acceptance and deployment. And obviously, one of our close partners on this has been Rick Stevens, the Argonne Associate Lab Director. I know Rick is showing up, I believe, tomorrow. His daughter was graduating from college this weekend, so obviously he prioritized that. But he has an important announcement, so he dialed in and gave us this exciting news I want to share with you as well.
Thanks, Jeff. It's great to see all the progress on bringing up Aurora and some of our early performance results. To help drive machine stability, while we work towards acceptance testing, we're going to be using Aurora to train some large-scale open-source generative AI models for science. Aurora, with over 60,000 Intel Max GPUs, a very fast I/O system, and an all-solid-state mass storage system, it's the perfect environment to train these models at scale. We formed an international collaboration led by Argonne, including Intel, Hewlett-Packard Enterprise, other DOE labs, US international universities, nonprofits, and international partners such as RIKEN to work together on this project. Our goal is to train and evaluate a trillion-parameter model on a large corpus, including general text, code, and scientific text, and building on our Gordon Bell work, we'll also be training on trillions of tokens of structured scientific data, covering many fields such as biology, medicine, chemistry, materials, climate, physics, and X-ray science. We're going to need lots of help to do this. Hackathons focused on these models have already started, and more are scheduled for the summer and fall. If you're interested in participating, please contact us. I'd now like to introduce Professor Satoshi Matsuoka of RIKEN, who will share more about their role in the effort.
Great, thank you, Rick. Satoshi-san, thank you so much for joining.
Thank you. Thank you. Pleasure to be here.
It's great to have you on stage always. Can you tell us about how you envision some of the work that Rick was just mentioning and the work that you're doing with that can advance science?
Well, firstly, I'd like to mention that Intel, as a company, and RIKEN, we just signed this overall collaborative agreement. Your boss, Pat, came over to Tokyo, worked with my boss, Nonokami-san, And we signed this treaty to basically work on future of computing, including quantum and AI, and also our future machine that Fugaku next we envision for 2029. But in the meantime, of course, AI for science is very important. As you may know, we're a national lab, the top national lab in Japan. We have thousands of scientists. We have tens of thousands of collaborators worldwide. But a lot of researchers in WECAN are really excited by the opportunity of this AI for science is bringing onto the table, well beyond what people imagine, the use of generative AI for writing beautiful emails.
How do you see it changing the way that science experiments are done?
Yeah, for one thing, of course, AI, as you had mentioned, AI is accelerated by HPC, but HPC is being accelerated, and science is being accelerated in many ways. So I'll just give you two very brief examples. One is by use of surrogate techniques. There's one earthquake code, and by the way, earthquake is very important for Japan, as you might know. Earthquake code, we have a brand new technique to have a very numerically accurate surrogate accelerating one of our latest earthquake codes, which runs on 150,000 nodes on Fugaku, by the way, so it's a very scalable code. And the code achieves effectively a speed up of 25x over the 40x we achieve over the K computer, or 1000x over K. So the code is already achieving 10 exaflop, effective 10 exaflop performance. And when we get to the next generation, this will be one of the methodologies by which we can accelerate code to zettascale, right? Effective zettascale. The other is more of a science fiction-y thing, if you can call it. But this one work, we're using combinations of brain simulations, very accurate instrumentation, but also use of the latest techniques regarding generative AI, large language models, to essentially transport the brain over to cyberspace, which you may see in science fiction.
Now you're scaring me.
Yeah, but it's true. I don't have time to go into details, but the combination of these techniques allows you to do the complete scanning of the synapses, the synaptic connection between the neurons, and then replicate, and then do segmentation, do all the replication using all the latest LLM-based segmentation techniques. And then we can simulate it on Fugaku very accurately, effectively transporting your brain into cyberspace.
Wow. All right. Well, that sounds like it will truly transform science and society. So look forward to that. Thank you. Thank you
very much.
Thank you. Great seeing you. Okay. We've had incredible changes over the past year. Science and the world, as we just heard, those advances are being supported from the underlying hardware. 4 new products launched this year within the last 12 months supporting HPC and AI. We've advanced the One API ecosystem, and we're making significant progress on delivering at scale with the Aurora system readiness. The question to us all is, what will the next 12 months bring? That's for all of us to deliver. Thank you so much for your time. Have a great night.